Oh shit. Ta-da. Okay, how's everyone doing?
Good.
Good. Everyone enjoy their 1 week break from this class? Too much. Y'all party too hard? You don't even remember what fluids are? Okay, all right. Maybe I shouldn't ask that. All right, so yes, the schedule will be updated. In fact, this doesn't work anymore because we were supposed to start computational fluids last Wednesday, and we didn't even finish talking about conservation of energy. So we have to do that first. And I'll try and adjust this. Maybe I was a little ambitious in my goals for getting through content. That's fine. And so we'll talk about doing the first check-in today at the very beginning of class, and then we'll go over a lot of the concepts. I'm seeing more people in office hours, which is good. And I'm trying to get through a lot of your progress reports to answer some questions. So if you have other questions, do let me know. Any questions about the bureaucratic side of work before we start? Okay. So let's jump right into this. Please work. Okay. What's going on?
The computer wasn't working for a moment.
Okay. So when I was in Berkeley yesterday at Space Science Lab, I went into the PI of Maven's office, and she has on her bookshelf, like one of 6 books, 5 books. What's this one? Oh, interesting. And look at how many tabs she has in it. So if you want to run a $500 million mission one day, maybe you too should consider what we learned in this class. Oh, I don't want to do that. Okay. So let's talk about the check-ins really quick. We're going to push them to next week because 1, we don't have that much material. I know you think shit tons of material. There isn't. As I was talking to Reed about earlier today, the amount of content that we've gone through, getting up to the continuity equations, getting through Navier Stokes, getting to conservation of energy, that could be a whole class, right? You could derive it with all the math. And we've kind of just sort of waved our hand at the math and said, let's do the applications. So necessarily, we might de-scope some options of what we cover. If something's really important to you and you want to see it in the text or this discussed, be prepared to talk about that, right? What your personal learning goals are. We're going to learn about computation. If you already don't know about that, that's a time to reach out to me and be like, what should I be doing on top of all the shit that I'm already doing in order to not feel that I'll be 1,000 feet behind the rest of the class. Vice versa, if you're really good at computation, but you have no idea about fluids, you reach out, you say, look, I'm really stuck on this. How do I get better at it? So that's the first part of the discussion we'll have. Whether you're close to your learning goals, about where you think you should be at, or whether you're well in excess of that, what I and you can do to improve your learning, and then what metrics you'll be using throughout the semester to justify your grade. You won't get a grade tomorrow or the next day or the next week, but you're going to get into the practice of checking in, seeing how the class is going, and seeing how you're best suited to learning. Because ideally, the point of class is to learn. Okay, so if you're not doing that, I need to know. Okay. Questions about the process? So I had a couple of people already reach out. I appreciate it. Just check in with me again. You'll get first dibs for your 5 to 15 minute session. Okay. It can be online, it can be in person, I don't care. Anytime before 10 p.m. and after 10 a.m. Because I ain't doing just shit until I've had a lot of coffee. Okay. All right. Before we do this, let's get our brains working. I know, fuck, I don't want to do that. But we were talking about stresses and strains and rotations And the big picture here, the things that I really want you to think about is when we talk about classical mechanics, we tend to think about making a formalism that allows us to interpret any problem. And essentially what we'll be doing with fluid dynamics is we are saying a few simple statements, and we're going to talk about how complex these statements become and why that can explain almost all fluids. So we have something like mass conservation. Normally you don't have to say that, right? So if I just throw this piece and I need to describe the kinematics, the force on it, the acceleration, you never really say dm dt because you just assume that the piece of chalk is in fact not going to lose any mass. Whereas the fluid can, or can deform its mass in a meaningful way. And we already saw that with the continuity equation. Same thing's true of momentum. Momentum is imparted to objects through what types of forces? Yeah, momentum is imparted to objects through what types of forces? Pressure forces, good. Pressure forces act on the body. Anything else? Gravitational or body forces, very good. What's another example of a body force? What's that? Gravity is one that acts on the body as a whole. One that we won't cover in this class. Air? No. What did you say? Air? No, no. It will act on air, but no. I'll include this TikTok on Monday. Electromagnetism.
Okay.
Right? We're not going to do that here. That's too complicated. And then the third type of forces that we're going to think about, these are the ones that everyone hates. Strains and stresses, very good. Now remember that strains are the result of how the fluid parcel deforms. Stress is what causes the deformation, right? Stresses can cause rotation. Okay. So I want you, we're going to warm the brains up. Okay, we have a cup. Perhaps it's my cup of coffee. Wow. It's flat. As I rotate it, what happens? I rotate the fluid with my spoon.
Gonna hug the edges.
Gonna hug the edges and make a whirlpool like that.
Yeah.
Did I do it right? Or should it be like this? Okay, why is that the right solution? Down and up? Yeah, that's correct. But why is that the right solution? Conservation of mass, and we can think of that as like conservation of volume. So if I go down here, I have to go up in the same amount, right? Same way of thinking about it. Okay. So we found out what the free surface looks like at the boundary of two gaseous bodies. Gaseous body, fluid body, sorry. Both fluids. Gaseous, liquid. Okay. What's the velocity flow look like throughout the entire thing? Where's the velocity zero? Where is it moving quickly?
Moving
Yeah.
quicker and would zero be in the middle at that point?
Yeah, you might have a zero here. But what kind of zero is that?
Rotation.
Okay, so maybe no rotational. Is there a radial velocity there? Let's say that this is our radial direction. This can be our z direction. And then omega or theta will be around that rotation. So as we spin it, everyone agrees that we are creating a vortex, good, and that has what kind of properties? Just broadly speaking.
A faster velocity as it goes towards the center. I thought it was the other.
Oh, it's just-
Oh, no. I thought it went that way.
Yeah, so here's the interesting part, right? If I'm draining it in a bathtub, it speeds up as it gets towards the bottom. But here I'm moving the whole fluid. Imagine I'm moving the whole fluid together, right? This is an idealization. because in practice, the fluid flow at the boundaries, right, has to be in contact with the boundaries. So let's say I'm moving the whole thing together. The velocity is gonna be the greatest out here and 0 down here as far as the rotation, right? Because it's rotating around the axis, and we know that it's omega r. So I have some omega component or a theta component, and then a radial velocity. Okay. What's counterintuitive here? What happens in z? What's that? Part of it goes up, good. Let's say this is now steady state, it's rotating, and I make that shape. How would you describe the streamlines? Can anyone just guess? Do they go like this?
That feels too simple.
That feels too simple. That's correct. It does feel too simple, and it is too simple. Because where do we have a problem?
On the edges.
The edges at the top
Very important.
and the bottom. The bottom is the place that's going to fuck us up. Right? Look at it. Okay. If I draw this streamline here, what happens to this flow? Is it really not moving? The whole cup is moving. This is supposed to be continuous. We have a real problem. Okay. So let's imagine now. I have two fluids. Okay, one on top of the other. The one on the bottom is heavier. What shape does the bottom form? Like this?
Yeah.
While rotating?
Oh, wow. Would it?
Yeah, so I have two fluids. Let's say I have light liquid on top of dark liquid. And I start to rotate the cup and I form this on the top. Everyone agrees this is correct, right? Anyone raise your hand if you think that's incorrect? And then I have this fluid on the bottom. Does it deform?
It should deform a little bit.
Heavier fluid?
This makes me think of like the lava lamp, where there's like two different materials.
Lava lamps are not necessarily always heavier. Remember that they go up because they're light. Yeah. Water and oil. Okay, let's do that. Let's do water on top of oil or oil on top of water. So there's two different fluids. They're not mixing. So is this correct? Should they what? Okay, so I'm gonna have 3 votes here. That one? Okay, any other choices?
I'm thinking that like some of it,
You like, what do you like this?
probably, yeah.
All right. That's what you want?
Yeah.
How confident are you? 50. Why do you say that?
Because trying to think how water interacts with air, since it's denser, it like pushes it up. So I think it's act the opposite in oil.
Okay, the heavier one's on the bottom here. Like here?
Yeah.
Okay. Sorry, go ahead, Desiree.
Oh, I was thinking like, kind of like a vortex in when it rotates, you think when you bring it up. Maybe like a-
Yeah, so maybe it goes all the way down like that.
I was thinking, look at the picture on the web, that like those little corner pieces. Like, what fucks it, so like, if it's like pushing down, like, just look at all those arrows, like, for the dotted line on the left picture.
Yeah.
Going down, is that gonna like push, like, you go back to the right image? The sides down,
You push it down here?
Yeah.
Yeah, it's a good question. Okay. So this is called the tea leaf paradox. And we're gonna watch it. And it's gonna blow your mind. Because Kobe's right.
Whoa. I guess.
But why? Okay.
The liquid at the bottom here is clearly more dense than the liquid on top. We know that because it has sunk to the bottom. But surely, if it is more dense, then when we swell the container, that more dense liquid at the bottom should be flung out to the sides. But instead, it seems to bunch up in the middle like an inverted whirlpool. To me, that's really counterintuitive. But if at this point you're thinking, actually, no, that's what I would have expected to happen, that is not counterintuitive, that's probably because you have had life experiences similar to this. Specifically, if you've made tea using loose leaf tea, or if you've added sugar to a drink. When you stir tea leaves in a mug, they tend to gather in the middle of the mug. That's why this is often called the tea leaf paradox. I'm calling it the inverted whirlpool paradox because I think it sounds cooler. You may also have experienced this effect when adding sugar to a drink, but in any case, maybe life experience is telling you that the heavier thing moves towards the middle when you stir it. But if you think about it, surely the heavier thing should move out to the sides. Like, that's how a centrifuge works. You spin the liquid and the heavier stuff moves out to the sides. If you're still not convinced that this behavior is weird, consider what would happen if I replaced the less dense top fluid with an even less dense fluid, specifically air. In this case, look, the more dense fluid does indeed fling out to the sides. I've actually told you what these fluids are yet, have I? The fluid on the bottom is water. I've dyed it brown, fittingly, with tea leaves, and the top fluid is white spirits.
So what's happening? Yeah, what does that mean? Okay, so you saw something really interesting there. You saw down like this and up like this, right? And when you really get it going, you can almost get them to touch, right? We have to remember that the whole system is complete here. So we can't just chop off the bottom of this because there is a bottom and there's a velocity gradient at the bottom as well. So there has to be full circulation. This is rotating in this direction, right? Then as this moves faster, okay, as it goes up, you're also going to have circulation like that. And so the circulation has to be complete. So it pushes out, down, over, and up, counterintuitively. Okay, yeah.
It seems like similar to like convection, that when something hotter and colder, like, it goes through a cycle.
It looks circular. There will be a lot of circle type things that we'll see in fluids, but this is not convection.
Okay.
So the reason that we're just talking about this now is that I really want you to begin to think about when we're doing these process of deforming the container in a way, or the parcel in whatever way we think we understand, we have to allow for the possibility that it will be counterintuitive. Okay. Some deformations won't make as much sense until you realize that any pressure that I apply here is propagated through the whole medium. So if I have here a free surface, right? The pressure here is greater or smaller than the pressure here. Why is it smaller? Yeah, what is the pressure due to at the bottom of a glass?
I think the pressure.
Yes, but what is the pressure due to? Everything above it. So the column here is shorter than the column is here. And now I have a high pressure system here and a low pressure system here. And when I just look at those two things, which direction will fluid move? From high to low.
That's so weird.
Oh, shit. I get it now. This all makes perfect sense. He's a great teacher. Let's stop learning. Does that make sense? Yeah. Okay. So in fact, we're going to use the continuity equation. We're going to use the momentum equation to solve things that seem counterintuitive, that seem trivial, And you're like, why would I even study that? That's stupid. And then we'll solve things that are really cool, like whether or not a surface of a star has an atmosphere. People who've done the homework know what I'm talking about? Okay. All right.
The liquid at the
Okay. Shit. So we have to talk about math again. You guys remember what math is? No, I hate it. Okay, so we were talking about 4.35. So let's brush off our old brains. Maybe just mine. And we are going to write the generalized stress tensor for an incompressible fluid. So Tij is equal to minus P delta Ij plus 2 U S Ij. What does that mean again? To go one step backwards. Hold on, let's write one more. Let's go backwards. Let's write it here. Tij is equal to minus P delta Ij plus 2 mu Sij plus gamma Smn delta Ij. Okay. So what the fuck are we talking about? No clue. What is T?
Stress.
Very good. That's quick. What's S?
Strain.
Strain. Okay, we're getting it. What's SII?
The non-diagonals?
The non-diagonal. So what does that mean? Yeah, show me with your hands. Yeah, different way would be this. Okay. Remember, we have a box. So I'm looking at the faces of the box. So this is SII and this is SJJ. What's SIJ? Two hands. SIJ, right? Right? Okay. Okay, does that make sense now? So this first term means what? First term here?
That's pressure.
It's a pressure term. Okay, so imagine I have a fluid, a box, and on the different locations, there's different pressures. Has that ever happened before?
Yes.
Yeah, in fact, we just saw it over here. You could have a box right here in the middle, in which the pressure on the left-hand side is less than the pressure on the right-hand side, and that would cause a force. Okay. That's P. What's this one? What? What's mu? Mu is a term. We're going to define it in about 2 seconds. It's a strain, good. And how does it look? 2 mu, very close. What's that? Yeah, it looks like that, right? Because it still has all of the functional form that it's allowed to have. In fact, Ij here could adopt any of the values of I and J. Not surprising. So it looks like a generalized strain. But what is this fucking one? That's weird. So if I and J are different indices, what's the Kronecker delta?
Oh, 0.
It's 0. So this term disappears for the off-diagonal IJs. Okay. And this is actually the volumetric strain rate. So this is how much it's allowed to compress or rarefy in each direction. Okay. So the reason that I wrote it over here, somewhat simplified, is just if this condition is true. Okay? No. Okay or no?
Isn't that a Stokes assumption?
Very close. So Stokes' assumption is a combination of these weird parameters. So you'll notice there's something called something called lambda, something called mu, and we haven't defined them. Right? But I told you that when you see them, we're really talking about viscosities. So this is a molecular measurement of how the fluid is dispersing the property that we're thinking about, in this case, flow. So as I act a force on something, how is the flow distributed in each direction? Okay, so you can talk about something like the bulk velocity, or sorry, bulk viscosity, which looks like this. Really good use of letters is gamma. Okay. That's the coefficient of bulk viscosity. It has a little bit to do with the viscosity and it has a little bit to do with the kinematic viscosity. They're just different. These are properties of the gas you measure. Okay. Yeah.
So the term on the left side is bulk viscosity.
This thing is called the coefficient of bulk viscosity.
Oh,
And what we use in general is a generalized stress tensor, 4.31 or 4.36 in your book, using the Stokes assumption, because it's pretty much true in places that you don't have shocks, that this thing, right, Stokes assumption is equal to.
oh,
Make sense?
What's it case when it's not zero?
I'm trying to think of a good example for you when it would be non-zero. I think you're mostly just talking about very immiscible or very viscous fluids. Fluids under a lot of stress is definitely not true in places where you have shocks, but a lot of this breaks down when you have shocks. It's all about just communicating the fluid force as well. This is just. Okay, and essentially what we get to is something similar to this equation on top. So we can say something like Tij is equal to minus P delta Ij plus tau Ij. Now you may not remember tau Ij, it's been like 16 weeks since you saw it, but that was, what was that again? Yeah, those were the stresses, remember? Those are the original form of the stresses before we broke them into strains and rotations. It was all encapsulated into that. Yeah. Oh, okay. Sorry. Okay. And so we can write this in a very complicated way. We can write this as being equal to minus P delta Ij plus 2 mu Sij minus 1/3 SMN delta Ij plus mu SMN delta J. Okay, you're really upset. You're like, why are we doing this? Right? It's stupid. But the thing that I want to show you here is something that is counterintuitive. Is what we've shown is basically empirical. We've made some statements that stress is related to the derivative of the velocity. I just said that, and you trusted me. The result essentially is that the stresses and the strains are linear. Stress, strain. Stress, strain. That is the definition of what type of fluid. Not quite. Yeah. Okay. The very beginning of the semester, I talked about all different types of fluids, and we talked about ketchup, and we talked about hot air balloons and shit like that, right? And I said something along the lines of fluids can be different, and we categorize them differently on how they respond to forces. So on one side, we say something like the stress, which is a measurement of the forces on an object. And on the other side, we say something strain is how it deforms. So I have a parcel of fluid. The way that it deforms is the strain, and the stress over here is the thing that does the deformation. They're the same type of unit, right? So here, I'm saying they're linear. If I double the stress, I'll double the strain. What type of fluid is that? One that behaves normally, exactly right. What would be a version that didn't behave? Non-Newtonian fluid. Okay, so if, for example, right, the stress is here, quadruple the strains, right, then you'd be like, oh, that's weird. Or if I stressed on it and the strains went down by a factor of 20, that'd be weird, right? Well, that is what Newtonian fluids are. It's the empirical relationship between the observed strains and stresses. Okay, shear stresses are nonlinear in a non-Newtonian fluid. Okay, so I have shear. Oh shit, that's really came out really good. This is the word shear velocity, even though the A and the R are together. So as shear velocity increases, right, the shear stress increases. Okay, so where's non-Newtonian in there?
Is it the one that it's Greg pointed out?
What?
Sorry, concave up.
Concave up?
Yeah.
Let me say this differently. Where's the Newtonian fluid? The straight line. Okay, so anything not the straight line is non-Newtonian. The one that we thought of originally, like oobleck, where is that? Well, they all go to the right. Can you?
Yeah, it's the lower one.
The lowest one. Why?
Because like if you hit it, it like cracks, right? So that means it's resisting, which means that there's less stress. No.
Okay, hold on. So resisting is not quite the way we want to think about it, but you're on the right track. So you hit it, and what does it do? Well, hardens is how we feel it, but let's describe it with the velocity, with the strains, with the stresses.
The high velocity gives it a high stress tensor. So the one that goes off the top.
High velocity gives it a high stress tensor.
Because it's because the compressive force is a lot more than if it just like with water. Kind of.
Okay, yeah. So let's let me see if I can. I feel like I'm maybe confusing folks for a second. So see if we can ratchet back the ideas here. For n less than 1, I apply some shear velocity. The resulting shear stress is magnified. And when I thought of that example, I told you about ketchup, where if you apply a force, the viscosity effectively goes down. It's more likely to move when you apply a force. Does that make sense? I mean, not know why it does that, but does that idea make sense? Whereas when you apply a force to the oobleck, it's less likely to move. Right? It was more likely to move when the forces on it were small. You apply shear to it, then it instantly takes all of that force and it sends it into the material, right? Making it hard. Make sense? So yes, this one here, in fact, the one that you said, is your oobleck. And this one here is your ketchup. That makes sense? Pseudoplastics are the ones that are going to convert shear velocity to shear stress. Okay. Okay. So we did it. You don't know what we did, but we did it. We have a generalized stress tensor. Let's not do non-Newtonian fluids. They suck. But they're fun to play with. They're horrible to model. Because in general, we want to just derive things in terms of the differential equations. And differential equations with powers are a lot more annoying than differential equations with just x, for example. Okay. But I want to show you really quickly that we'll build it over here. Okay. So we had this weird thing. Right. What's that? What did I write? Yeah.
Is that, equation of motion?
Okay. What does that mean?
That means that the total derivative is equal to the body force of the current system.
Okay. So we said this is the body forces. And this is the stress. Okay. The reason that we did any of that shit having to do with stress is because we didn't know what this was. So we need to define it in terms of things that we can measure. Strains are defined as derivatives of the velocity flow. So we can fully define the stresses, and we can just chuck them into there and we have a whole bunch of derivatives. Okay, what was the left-hand side? What did this mean? It's a total derivative. What was that derivative? Does that mean conceptually? What is the total derivative here? If I differentiate this. And I do this maybe every class.
How it changes in space and time.
How it changes in space and time. So what do the two terms mean? Not what are they, but what do they mean? What? Steady. Well, unsteady and advection. What is that word? Yeah, let's not call it heat, because we're not talking about heat. But it's the transfer through. Yeah, through space, through objects, through. What's doing the transferring?
Well,
The flow is doing the transferring. So instead of it just changing in time, the flow is moving, the property is moving. Okay, so advection. Okay. Conceptually, that's what dBq means. This is the total time derivative of what property? Density times velocity is the in fluids.
velocity.
Fluid velocity, I see fluid velocity, I see density. What is that together? In kinetics, we would say MV is the. What's that? It is the momentum. In fluids, we think of the momentum as the product of U with rho. How would we think of the energy in fluids? If I use that same analogy.
Roll in the second derivative.
Sure, before we get to derivatives, just like, not the change, not the rate of change. But if I just said, I'm going to make a little library here, let's say I call U. Like that. So what would MV be? I just told you what it was. The momentum, how do I write that here?
Oh, rho times the total number.
Rho U.
Oh.
Okay, so how do I write?
So it's just squared,
It's what squared?
the total derivative squared.
Well, I haven't taken a derivative. Remember, this is saying the rate of change of the quantity. So it's U squared, right? So it's like this. That is the kinetic energy of the fluid. So we have these direct parallels to things that we do understand, even though we don't understand anything in the class, right? The momentum is the fluid velocity, sorry, the fluid density. Sorry. The mass is the fluid density, the top line. The momentum, MV, is rho times the fluid velocity. The density times the fluid velocity. And 1/2 mv squared, maybe I'll fix this because that looks disgusting. Is 1/2 rho U squared. And we'll see that just in a few seconds, but I just wanted to prompt this. So what that term is saying, what Cauchy's equations of motions actually mean is. Yeah. What about the fluid is conserved?
It's
Momentum is conserved. It is a conservation law, one of 3 that we will need. We have the first one, that's the continuity equation that says that mass is conserved. The second one that we've just derived is that the momentum is conserved. So the left-hand side says that the density times the steady and advective form of the velocity is only due to 2 items. 2 items. Body forces and gradients in the stress. Okay. We've defined the stress. And now we magically get to talk about something that you'll get to talk to all your friends about. You'll be so excited. The Navier Stokes equation. Okay. Same Stokes from Stokes with the function. Okay. So should we write it all the way out? Yeah, I guess we have to. We're gonna start with this thing. Okay, that's 424, that's Cauchy. Then we're gonna use that one over there, the bottom one, right? Gonna add water, get it? It's fluids class. Oh, not, all right. And then you get Navier Stokes. Okay. So what it ends up looking like is a lot. Okay. We'll see.
Good, right?
Yeah. Makes total sense. Good, all right, let's go home. So what did I write? What does any part of it mean? What does it look like? What does it mean? Oh, good, found a body force. Where is it? EG. E? A P, row. Hey. Now you don't have to answer any of the other terms. Where? Which one? It can't be like that. Oh, okay. Pressure. Where's the pressure? That is the P. Yeah.
That's the pressure, not the momentum.
What?
There's
This
momentum
is
itself,
P.
right? So we directly,
This is not a P.
yeah,
That's a row.
Yeah.
Okay. This is not a P, sorry, this is a row. See how curly it is?
momentum is always, well, nearly always, represented as P, right?
No, not in fluids. Maybe in like Lagrange mechanics, yeah. That's just because we run out of letters.
Okay.
Yeah, sorry. So that is confusing. In this case, P will never be the momentum. It's always rho V. And you said stress, where did it? Okay, what does stress mean?
The force that is exerted on the fluid,
Mm-hmm.
how it springs out.
Force that causes deformation.
Force that causes deformation. Read, did you have any?
I haven't been to.
Yeah, what does it mean?
You're experiencing right now.
Okay, whenever we talk about stresses, the way to see where the stress terms are is because they have our favorite friends who don't make any sense, right? Which are what? I's and J's. We should get I's and J's. In fact, we're going to talk about what that means here, but it's these things. It's the mu's and the lambdas, right? Mu's and the lambdas are talking about a material property in the fluid flow itself, which is doing the transfer of momentum within the body. So whether that is compressing it, whether that is pushing it towards itself, straining it in this way. So where are the terms there? Right, okay. So on the right-hand side, all of this stuff is Tij, which in fact, hey, looks a lot like this. So this pressure term came out and went to the front. And this whole thing went all the way over here, where instead of writing it with S's, it's derivatives of the velocity, which is the initial definition of strength. So the thing that we wanted to do here is I have these mu's and whatever, mu naughts, that's fine. But what I want to show you is how the tensor notation works here. On this left-hand side, I have dui dt. Okay, so this would be three equations. This would be an equation for x, y, and z, for example, whatever your three principal components are. Or it could be r, theta, phi. I don't care. And this one here is u in the direction of that first component. And that's equal to all of this stuff when the i's cancel out. Did I write this one? Yeah, I did right around. So when the eyes cancel out, when you see repeated indices, these parts are going to disappear and they're going to be left with whatever the remaining index is. Does that make sense? Okay, how they cancel out. They will just in a vector notation, when you write something with multiple repeated indices, you're only going to be left with the component. So let's say you have a dxi, it's supposed to be a j, that is only going to be in the direction of j. And as j takes on properties of x, y, and z, this would be only the x component, or the y component, or the z component. Right? So because there's no i's here, right? It's going to disappear. It's going to be a scalar constant, dxgi, right? Whereas this is a vector in 3 dimensions.
So in that case, we would have to write out this right hand side, like in a matrix, in order to get every dimension.
Yeah, so you're getting to the part that's really important. Okay, so this is a really good point. On the left-hand side, we have du, dt's, right? You have dx, d partial u's, partial x's. We have multiple versions of this. You want to solve for your velocity in u, your velocity in v, and your velocity in w. And it'll be due to all of these things and all of the directions that matter. Does that make sense? So for example, the body forces in xj, they're also important when you think about the fact that this has a direction here, which are the gj's, right? So if, for example, I'm looking at how the flow changes, let's call it the y direction right now, I'm going to have pressures in y. Those are the ones that are going to balance out the gravitational forces. If I have a gravitational force that's here and this way, then I'll have to think about them separately. The pressure forces in this direction are going to be balancing the gravitational forces in this direction. And it'll lead to changes in the fluid in that direction. Does that make sense yet? Or is this all confusing? Okay. So imagine that that's totally not there, right? That would be, say, your undergraduate 2510 Bernoulli type equations with pressures and gravity balance, right? All of that disappears. You're very happy. So this piece can still make sense to you. And in fact, it will reduce to Bernoulli's equation once we make some implicit approximation. Okay. But this is totally general. And all of these terms mean something. Okay. Well, what's nice is that you just have them. So for example, these are derivatives. We love doing derivatives. It's really easy. Right? Integrals suck. Derivatives. Okay. Okay. So let's talk about some formalisms where we can simplify these equations so that they're actually helpful. Well, actually, wait a second here. So let's do some math. Let's put. There's 3 of those, right? 3 equations is a vector equation. Is that true or no? Let's make one point really quick. What is the momentum equation? What is the continuity equation? Anyone have it? At the top of their head?
There you go.
Mhm. You like this? That's it, right there. And we made some simplifications, right? We said like rho is constant or some other stuff like that. And then we were allowed to do fun things with it. Okay, and I said that repeated indices are going to cancel. So that's one equation, because here it's del rho dt, and this is just the rate of change of the density compared to how the mass is moving around. So that's one equation. That's three equations, right? We already said that. We have an x, y, and a z. Okay, so now I have four equations. The problem totally solvable? But the what?
I guess the number of variables that.
Good, so how many variables are we getting? Okay, we need to know u, so u, v, w. Because those all depend on the position, right? Anything else? Rho. What's x? X is just the location. That'll be our independent. Mu will be a property of the fluid. We'll hope that it's not changing. Time is another independent variable. Right, just like space and time, we're thinking about this like lattice. You got a box, and you want to know the properties inside that box. Okay. No, because this is just a function. It's just an indexing function. What was it? Pressure. Very good. Okay. Okay, so we're back. Right?
If we had forward,
We have four equations and we have 5 variables. Oh no. But what can I do if I'm clever? Good guess. Incorrect.
make an assumption so that one of them goes to 0.
Okay, so we can either say one of them goes to 0, right? So rho is constant, could be something like that. The derivatives of rho will disappear. Or what about if pressure and density only depend on each other and not on temperature? Right? Was there ever a situation where rho was proportional to pressure? Yeah, what was that? Close, but ideal gas laws depend on temperature, right? E equals. Oh, let's see, rho Kc. A long time ago. Many moons ago. So we said something along the lines of rho and P were proportional to a constant. And there were some other numbers involved, like an adiabatic gas. Yeah, that would be the adiabatic gas law. That directly relates the pressure and the density, but not through the temperature. Right, when a gas is adiabatic, then I'm done and I don't need an energy equation. But in general, because these will in fact be related through temperature, then I'll need to understand how temperature turns into pressure or changes in density, right? So first we'll play with the Navier-Stokes equation and look at some simplifications. But in general, you'll need another conservation. Okay. Anyone feel like they want to try? Just in the back. Yeah. So let's talk about some simplifications. When the flow is incompressible, how do I write that? Like in math terms? Yeah, when a flow is incompressible, that's the words that I'm using. How do I write that in math way? What?
TII equals 0.
No, because you can still stress it without compressing it. It's close though, you're on the right path.
Is it when that derivative is 0?
No, not quite.
Is there a like, let's stress this, is there something?
Yes, there's definitely something inside of the stress tensor that becomes 0. It's these terms, right? And another way to say these terms go to 0, that I can't compress it, not compressible, is to say the divergence of the velocity is 0. That, for example, the du dx terms plus the dv dy terms are all going to equal 0 when you add them together. So if I do compress it in x, it has to expand in y. That would be an incompressible fluid, right? It's not just saying that I can never press it this way. It says that it'll move out of the way if it's incompressible, right? Right? Okay. So in fact, that helps because that gives us the simplified form of these equations, which is beautiful and actually usable. So if we just say something like, then I can just say, and what are the terms mean? What is this GDT? Big D over big DT? It's what? It is the momentum, yeah. So this is the mass. It's the density times the velocity, which would be the momentum in our case. But what is the big DT? The total derivative, which again is the steady and the effective terms. That's those first two terms you saw in the top right-hand corner, right? Okay. I haven't done anything. I just made it into one equation. That's a vector equation now. And the first term is the gradient. That's the same way as writing that gradient over there, but in index notation. Just showing you two different versions. Index notation, vector notation. Okay, second term is the body forces. Same term, same term. Okay, okay. So what did I change in that last term? Yeah. Yeah. So open up the trunk and see what's inside it. Yeah. Okay, so here, I's and J's can be whatever they want. Here, what do I get?
You only get the diagonals.
Only get the diagonals because this is UM and this is XM. So M can only be the diagonals. And for an incompressible fluid, that means that this is 0, right? So in fact, this thing can be rewritten as mu V minus del 3. And that's a butchery of vector and index notation. That's what I'm trying to demonstrate. So when I can make that term 0, then mu doesn't depend on x. That can come right out, and these go in. You get that thing. Nope. Okay, it doesn't look better. But I promise that it is. I promise that it is because what do we know about when you apply a Laplacian to something? When del dot u is equal to 0?
Wouldn't that also be good?
No, the Laplacian can now be a normal vector. In fact, we want usually the velocity to have some form. If del dot u equals 0, then del squared u equals what? Everything equaling 0 is not the answer here.
I already said 0.
Well, the other options are constant, right?
No.
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 I don't think any of those things actually 0.
Yes, remember it's a vector quantity. So all of the terms, when you do the divergence, right, they'll cancel each other out, incompressible. So we talked about with the fluid going this way becomes the fluid going that way. Okay, that does not mean that the slope of the velocity, right, which is what this is talking about, or the acceleration of the velocity, is always 0. In fact, you get this funny thing again, remember? No?
That vorticity.
What?
I was gonna say like that vorticity.
Yes.
Okay.
Weirdly enough, vorticity is here. That's what I wrote there. What the fuck is vorticity doing here? How did you show up? Well, it turns out this is a great thing when you talk about vector fields, because vector fields have this property where if I take the gradient of a cross product, or if I cross the gradient of a product, something like vorticity, that will be equal to something that when I take the divergence, it'll disappear. Right? I think it's minus. I mean, I can write that out in more detail, but that's fine. Actually, don't write that down exactly. Let's write it properly, so it's not written. Good like this. Okay. 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 So we're almost there. Let's go back to like when we had a really good time and imagine that you don't have any viscous forces. What do you got? What? Yeah, you're pointing. What does that mean? Euler's equation. Yeah. It's okay. So Euler's equation looks like what? Yeah, boom, erase the last part, right? Euler's equation here. Very straightforward. ddt, pressures, and body forces. Boom, we're done with Euler's equation. Okay. Is that helpful? We do most of the homework now? Okay, so let's pause before we talk about energy. People have questions on the homework that they want to see using any of these components. Has anyone looked at the homework?
Only on homework 3.
On the homework 3. Okay. Yeah. So we have homework 3 and homework 4, right?
Yeah.
And you're all turning in homework 3 like today? No. Okay, turning both in Monday? Yeah. Parameterize, yeah. Okay. Okay. Anything using these pieces here? Because we can talk about that definitely in like 3 minutes after the class. Questions about what we created today? Yeah. Mm-hmm. Right, so remember that when we're evaluating each of those, they have different meanings. What is a streamline? Yeah.
Like. It's like the.
Instantaneous, important word, at t equals a certain specific time. It's all the points of the velocity in the fluid, right? Tangent to the velocity of the fluid.
Streamlines don't touch.
Streamlines never touch, they can't touch. But it's instantaneous. So you take snapshots, the streamlines can change. Right? We saw that picture, the changing fluid. Okay, what were the path lines?
Where the single parcel of fluid went.
Right, so the life of a single parcel. So we take some place at x of, let's call it x naught, and then you have time and you let it run all the way through. So how does that single parcel move? What is a streak line? Not quite. A streak line is defined as all of the things that will pass through a specific space. So just like we talked about an instantaneous time period, we said, here's all the fluid velocity at that time, at all space. And then for path, we said at a specific parcel, what are all the places that it'll go through in all times? Now we say in a streak line, choose a specific location and which parcels will go through that in their life. Does that help your parameterization question?
Oh, I didn't know that was relevant to that.
Okay.
I'm sorry.
That's fine. But you're talking about 3.6, right? Okay, maybe we're talking about different problems. Yeah. Any other questions? Okay, so before we do the caloric equations, we'll pause here. We'll do calories on Monday. And then hopefully we'll get into computation. We'll see. Kind of slow, it's okay. Questions, comments, concerns? Okay.
Supposed to like appointments with you to argue our break this week.
Yeah, that was at the beginning of this class. We put up hold on, let me stop the recording.